Hello students, the topic which we are going to discuss today is techniques for Turing machine construction. Okay. So, what does this mean? Techniques for Turing machine construction is we are going to discuss the concepts which are essential for the working of the Turing machine, what things are required for the Turing machine to be constructed or to design. Okay. So, there are 4 concepts here. By using all these 4 only a Turing machine will work. Okay. So, first one is Turing machine with a stationary head. Okay. We know what is the structure of Turing machine. Okay. Normally this is an infinite tape, okay, which is Turing machine is a theoretical model. Okay. It resembles the computer. So, whatever problem you want to do on the computer, you first analyze it, you first analyze whether the solution is there to that particular problem or not. Otherwise, if you simply give the problem directly on the computer, sometimes the computer may stuck, it may damage the working nature of the computer. So, first we test any complex problem on the Turing machine. If it is run successfully, if you are getting the answer correctly, then we implement that on the computer. So, first one is stationary head. Normally finite automata, the Turing machine is similar to the finite automata. You have a tape, okay, there in finite automata you have a finite input tape. Here we have infinite tape and we have a finite control, okay, and we have a read write head here. So, this will read one symbol at a time across the input tape. When no input is given, the cells in the input tape is completely kept as blank. So, the blank cells are indicated by using capital B or we may also use small b. Okay. So, whenever there is a transition, okay, some input is given and whenever we want to change the states according to the given problem, we can make this read write head move one cell at a time, okay, using, and we need to specify the directions also. So, that is what is given here. Whenever we are in some state, some input is given, we can go to the next state by replacing A with another symbol, okay, or you can also keep this A as it is, okay. It is not compulsory, depending upon the problem. Sometimes if any input is given, we will try to replace it after reading it and then we go to read the next symbol in the next cell, okay. And then we also specify the direction. This direction indicates that the read write head is moving towards either left or right, whether it is moving to go to the left direction or right direction to read the next symbol, okay. Normally this direction will be left or right. In case if you do not want to go to any state, any next state, if we want to be in the same state, okay, then we can also make the read write head to be stationary, and that type of transition we can write like this. When at state q, okay, an input A is given, okay, which is leading to a transition. If input A is given, it leads to a transition by changing input A to Y, and you will be in the same state S, capital S. That means you will be in state Q only. This indicates that if you give A, this will be the transition, but we are going to be in the same state. We are not making the read write head to go to the next state, okay. If we move, this will be the transition, but we are in the same state Q. So, this is about the stationary head. The head can be you can either move or you can make it as a stationary head. Second one is storage in the state. So, whenever we are moving from one state to another, okay, then how does the machine analyze that after reaching the final state, the total string whatever we have given is read completely, or the condition which is given is correct or not? It depends upon the storage across each and every state. Whatever inputs we are giving, suppose we are giving a string, okay, accept a string which is ending with 3 zeros, okay. So, how does the Turing machine analyze that whatever string we are giving, it is ending with 3 zeros? Across each and every state there will be a storage. So, depending upon that storage, it will analyze whether it is across each state this condition is valid or not. It analyzes the input across each and every state. If it is satisfying this, okay, it says the Turing machine will run successfully. So, it is based upon the storage at each and every state, and the storage is given by cube into the symbols which are present in the input tape, they act as the input symbols across each and every state, that we are writing it as q into tau, and this will lead to the new states, and that is called as transition states. Okay. So, normally we write capital Q into tau as small q into a. Small q represents the different states and small a is some input symbols which we replace across each of this blank symbol. Okay. So, by using these two only we do the transition. The next thing which is required for the Turing machine to be run successfully is multiple track Turing machine. Depending upon the problem, we can go for even multiple track Turing machine. If it is a simple problem where the string is in a linear way, okay, just a string is given, based upon some condition you need to pass the string, this is a linear way. So, in this case we require only single track Turing machine, that is single tape. Here a problem is given to us, like find out the multiplication of two numbers. Okay. So, the total tape is divided into three tracks here. This is one single tape. So, here we are trying to find the multiplication table of 4. Okay. So, y is going to change every time. 4 into 2, what is the resultant, that we are going to write in the third track. Then what is 4 into 3, that we are going to write in the third track. So, across each and every cell we have a storage, and for complex problems or for some scientific problems we use such type of multiple tracks, means a single tape is divided into multiple tracks. Here for this example we are taking only 3 tracks, but these tracks may be increased depending upon the complexity of the problem. And the next one is subroutines. These subroutines are also called as functions, like how we use in the programming languages functions. Whenever any calculation is to be repeated again and again, we put it in a function. So, that function is called as a subroutine here, and that will be executed by taking an initial state and return state. Now, what is this initial state is, whenever you want to execute a particular problem again and again, we go to that particular state where that function is starting, that is called as initial state, and from initial state the total calculation is carried out through a group of states, and at the final state, once the calculation is completed or once the function is completed, from that final state is called as return state. The Turing machine will enter into that return state. From the return state, once the function is ended, we are going to come out of the function and we are going to come to the next line of that particular function, that is end of the function. Like we have some function, we have some lines, again we have to return back to the program, main program. So, this total thing here we have the initial state, okay. So, where we are going to start, at the end we have return state. This return state, it will make the control to again move back to the main program, return the result to the main program, and then continue towards the successive statements after the function. So, these two functions, initial state and final the return state, will help the Turing machine to implement the subroutines. Okay. So, these 4 things are essential. Based upon these techniques or these things only, Turing machine will be working. So, this is about the techniques for Turing machine construction. Thank you.